point. Just go ahead and go down here. All right, so what we're going to do is I'm going to jump in and all right, we're going to for the first chapter 10 stuff, there are mainly two main topics in there. One is Lewis structures, the other is Vesper structures, you know, the valence shell electron pair repulsion, the three-dimensional version of Lewis structures. Now, the thing about Lewis structures is they are basically two-dimensional. They're not three-dimensional. Some people have added in little nuances to make them three-dimensional, but basically they're two-dimensional. So if we get a formula like, oh, let's see, C2, I'm trying to think here, I'm going to make that C2, H6O. Okay, if we look at that formula, let's do all the Lewis structures that we can, at least one. Okay, so again, the process is, first step is to take the most complex of the atoms, the carbon, hydrogen, oxygen, and put that in the middle. Now, what I mean by the most complex is the most singleton electrons, okay? But on the outside are all the ones that have singleton electrons, and that's the hydrogens. Now that could also be the halogens as well. They also have one singleton. So anything that has just one singleton electron is the least flexible in terms of different structures. That's why you put them around the outside. The ones that have the most singleton electrons, like carbon, nitrogen, etc., have the most flexibility. You can move them around the most. So that's why I always suggest starting off with putting them in the middle. And then we have what's left over is oxygen. Notice I put the pairs of the oxygen away from the center of the molecule, since they aren't going to be contributing to binding. Now the next step is to connect everything up with at least one bond. Okay. Did I do that correctly?
No, we have leftover electrons on the oxygen.
Yeah, the oxygen is totally not connected. So let's back off and do this a little differently. Let's here. Oops. So all atoms have at least one bond. Now the next step is, are there any singletons left over? No. That means we need to do the analysis now. Remember, there are two steps in the analysis. One is number of bonds. Carbon needs 4 bonds, oxygen needs 2, hydrogen needs 1. Okay, so carbon we have 1, 2, 3, 4, 1, 2, 3, 4. That looks good. Oxygen needs 2 bonds, 1, 2. Hydrogen needs 1 bond all the way around. So that looks good. The next test is full shell. Full shell in the case of carbon and oxygen. Well, let me back up. Everything except hydrogen is going to have 8 electrons. Okay, so we have, with oxygen, we have 2, 4, 6, 8, because we're sharing electrons now. Carbon's got 2, 4, 6, 8, 2, 4. So everything's legal. That means that is a legal structure. The next step is to then replace the bonds with solid lines. And that would be the legal structure. Now, there's another legal structure for this as well. The other legal structure would be putting the oxygen between the 2 carbons. Let's do it in a different color. Okay. And now we need to move. And we're going to take 1 bond per atom minimum. Okay. And are there any leftover singleton electrons? No. So we need to go to the validation step now. Validation step is we need to check for number of bonds for carbon, oxygen, and hydrogen. Okay, carbon's got 4 bonds here, 4 bonds here, left and right. Oxygen has 2 bonds. Hydrogen has 1 bond all the way around. Now check for full shell electrons. Carbon's got 2, 4, 6, 8. Oxygen's got 2, 4, 6, 8. Carbon's got 2, 4, 6, 8. So this is a legal structure. So then the next step would then be to add solid lines where all the bonds are. Now these 2 structures are very legal as far as Lewis structures go. The problem is chemically they're very different. This is called dimethyl ether, which is used frequently as not frequently, used to be used as a anesthesia. In fact, when I had my tonsils out back in 1953, I was put down with the ethyl version, diethyl ether. And I remember to this day, I was laying down very, very, very anxious, and they put this gauze over my mouth, and then a cloth gauze, and then they poured this liquid over that, and I remember going out. To this day, I remember that. That was almost 7 years ago. I remember that. Okay, and this is called ethyl alcohol, which is drinking alcohol. So we have an alcohol and an ether. Those are very different structures. Alcohols in general have certain reactions. Ethers have certain reactions. Alcohols tend to have higher boiling points than ethers. So there's a lot of wet chemistry you can do, excuse me, to figure out what structure you have if you have the formula C2H6O. Okay, how are you guys doing on that? Does that make sense?
It all makes a lot of sense to me. I need to do more practice because I still struggle to do these steps in my own brain, like to make these.
Right.
Yeah, but that's I think that's because I didn't practice as much as I should have.
Okay, but as far as the steps go, they make sense.
Absolutely.
Okay. All right. Any of you guys, other guys online, do you have any questions about the process?
No, not really, but I still need practice too.
Okay. No. Well, the The test is already been done, and it'll be available midnight on Wednesday morning. And you'll have, full 3 days, and I gave you 2 hours to do it. So, and it's multiple choice and true false. So, okay, let's do another one. Let's see. Oh, I don't know. Let's see. C3 and let's see. Making these formulas up on the fly is kind of an interesting exercise. Picturing the structure in my mind here. Let's see. The hydrogen. Okay, well, let's see how well my mind sees the structure. Okay, so let's go ahead and try this guy here. Okay, so you're going to have 2 carbons. And then we have 7 hydrogens. Okay. Go ahead and connect up 1 bond. Okay. There any singleton electrons left over? No, we have electron pair over here on the nitrogen, but it's already paired up. And by the way, just one little note. I think this may be slightly out of the scope of this class, but actually you can actually bond with that double or that pair of electrons. And you bond with an empty shell of another atom, and that's called a coordinate covalent bond. You will get into that in 400, and I think it's out of the scope of 300. I really think it is. It's kind of pushing it. But anyway, so basically, as far as we're concerned in this class, two single electrons will bond, and a pair of electrons we're going to consider non-bonding. But just keeping that way in the corridors of your mind, if you're assuming you're taking 400, that you can bond with a pair of electrons. Okay, so let's look at the number of bonds for carbon. We have the left carbon is 1, 2, 3, 4. Middle carbon is 1, 2, 3, 4. Nitrogen needs 3 bonds. We have 1, 2, 3. And looking at full shell, You have 2468 for carbon, 2468 for carbon, 2468 for nitrogen. So this is a valid legal Lewis structure. So the next thing we're going to do is add solid lines. And this is called an amine, by the way. You don't need to know that. It's called an amine. All right. Now, the one thing I'm going to notice here for you. In fact, let me just erase this real quick. What I'm going to do is now you can take this structure. This is not allowing me to rotate it. You can rotate this structure left and right, up and down. So if you wrote a structure similar to that, only you ended up with this. These are equivalent. Also, if you ended up with this. These are all the same thing. These are all the same structure. They all have single bonds between them all. The nitrogen attaches to the middle carbon on all three of these. It's just a different perspective. Now remember, molecules in free space can freely rotate. That's one of the modalities of movement or motion that all molecules will have, is they can rotate, they can vibrate, they can move from one location to another translationally. So those are all legal modalities of movement of a molecule. So when you're drawing these Lewis structures, all three of these are equivalent. So if we had an in-class test and I was asking you to write these out, if you wrote out any one of these, it would be fine. Now, we can also do this a little differently. We put the nitrogen in the middle between the two carbons. What would that look like? Okay, we have carbon. And then we have okay. So let's connect them all with one bond. Okay, so you can see the similarity between this and this one. With the oxygen in the middle, we have nitrogen in the middle. So we can get another isomer. This is called a constructional isomer or a structural isomer, because we have the same number of nitrogens, hydrogens, and carbons, but the structure is different. So it's a structural isomer, or sometimes they call it a constitutional isomer. Okay, so let's connect up the lines. Before we do that, is this a legal structure? We'll see we have 2468 for the carbon, 2468 electrons for the nitrogen, 2468 for the carbon. We have 4 bonds for the carbon, 3 bonds for the nitrogen, 4 bonds for the carbon. So it's a legal structure. So that's what that would look like. And this is called a mean. Primary mean. This would be called a secondary mean. And for this class, you don't have to worry about that. I'm just telling you the names. Okay. Chemically, these are going to act similarly because they're both the means, but not the same. Not the same. Okay. Okay. These are two-dimensional flat Lewis structures. And what we can do is we can then change our strategies on how to do structures by using the valence shell electron pair repulsion idea. In other words, we're taking those electrons based on the repulsion to one another and make the most stable structures. And that'll be a three-dimensional version. Okay, so any questions about Lewis structures before we get into the Vesper structure?
Professor, are you okay with the, oh, sorry, you can go first.
I was actually just saying I didn't have any questions. Thanks, Jacob.
Oh, okay. So what was your question?
I'm trying, it keeps muting and unmuting me, and my dog's about to bark at the mailman. Okay, I'm still drawing these diagrams with the dots, and I see how you keep changing it to the ones with the lines. Is it okay if I leave it as the dot, or do you want me to redraw them with just the lines with the connections?
Redraw, well, the last step is to redraw with lines.
Okay, I thought so. Thank you.
Yeah. Yeah, you'll, it just, one, it simplifies it, and two, you will always see Lewis structures drawn with lines. So yeah, just complete it. Any of these yellow connections, just replace with lines.
Got it. That's actually fairly easy. Thank you.
Okay, so let's take these same compounds now, and let's do this using the valence shell electron pair repulsion concept. Okay, so we're going to take this guy here. We are going to move it down to here. Okay, now this says valence shell electron pair repulsion. Okay, the key in this structure is electron repulsion. The idea is these electrons do not want to be by one another, excuse me, because they have the same charge. Identical charge structures, particles, repel each other. So if you can get them as far apart as possible, that's the most stable configuration. So the first step in doing a Vesper structure is to do the Lewis dot structure. Okay, so what we're going to do is we're going to redo that here. And then once you draw the Lewis dot structure, you need to ask, how many central atoms do I have? Remember, the central atom is an atom with two atoms attached or more. Okay, that means that carbon, carbon, and oxygen are central atoms, not the hydrogen. That means we have to do three separate analyses. So this analysis is per central atom. 3 central atoms, 3 analyses. Okay. So for the first carbon, we need to, this will be the first carbon over here. How many electron domains do I have? Remember, electron domains are groups of electrons. Now, remember before you took them and converted them to bonds, that was a pair of electrons, 2 dots. That's one grouping. Okay, so we have 1, 2, 3, 4 electron domains. Electronic geometry for 4 electron domains is tetrahedral. Bonding versus non-bonding. Well, we have no bond, no, we have no non-bonding. All are bonding, so that's 4 and 0. Let me go grab one thing from this is right here. Okay, so basically, we're going to be filling in from this chart here. Now, when you get to 400, we're going to expand this to 5 and 6 groups. So this chart will be further complicated, but the purpose is exactly the same, and the concept is exactly the same. It's just more options on it. So when you have 5, you have some more combinations. When you have 6, you have more combinations yet. When you have 5 electron domains, you have 4 different combinations. When you have 6 electron domains, you have 5 different combinations. And they all have their own little cutesy names and stuff. But for our class, we're just doing 4 electron domains, no more than that. Okay. So the second C here is going to be exactly the same. We have 4 electron domains. That means that's tetrahedral. And we have no non-bonding, so that's 4 and 0. So the molecular bonding is tetrahedral. Both of these. And the bonding angle for tetrahedral is 109.5. And lastly, we're going to do the oxygen. So the oxygen has got 1, 2, 3, 4 electron domains. So again, that's tetrahedral. Only this time we have 2 and 2. We have 2 bonds and 2 non-bonds. Okay, and the molecular geometry for that is bent. And the angle is significantly less than 109.5. And the reason the angle is less is because those electron pairs are pushing the other 2 electron bonds together. So these guys here are pushing on these guys, so that angle is less than 109. This guy is pushing on these, so this angle is a little less than 109. So if this electron pair does damage here, 2 of them does even more damage in terms of pushing those. Remember, we're talking about electrons repulsing one another. Okay. let's do another example. Let's do one we've already done up here. Let's do this guy here. You remember there's, each one of these has different structures. If we did, don't forget that was an alternative structure. So if we chose that structure, we do a slightly different analysis than this one here. They're going to be similar, but not the same. Same with this. Remember, we had a alternate structure as well. So let's do this guy here. So let's do the one with the nitrogen in the middle. Okay. So how many central atoms do we have here? Well, we have 1, 2, 3. So that means you're going to have 3 analyses. Now on this one here, the 2 carbons are going to have identical analyses, but there's still 3 central atoms, 3 analyses. Okay, so let's do carbon, nitrogen, carbon. Okay, so the leftmost carbon, we're going to have 4. That makes that tetrahedral. Okay, we have 3 bonds, 1 non-bonding, so that makes that trigonal pyramidal. Now, trigonal pyramidal is a 3 3-sided pyramid. Is a 4-sided pyramid. Hence the trigonal prefix. And that is going to be 109.5, but less than that because of the non-bonding pair of electrons. Okay, as far as the nitrogen goes, okay, we have 4. Actually, when I did the 3 and the 1, I was thinking of the nitrogen. Can't believe I did that, you guys. So that carbon is 4 and 0, so it's tetrahedral. And that'll be 109. And the trigonal pyramidal is 109.5, but it's less than that. I am very sorry. The whole time I was thinking nitrogen, nitrogen, nitrogen. Okay, and then the carbon down here is going to be the same as the other carbon. These are the same. So it's going to be 4 tetrahedral, 4 and 0. Tetrahedral 109.5. Now remember when it's 0 on the non-binding, these are going to be the same. When it's not zero, they're going to be different. Okay, so, and again, I gave you lots of practice on this as well, additionally. Okay, so let's jump now over to naming. Now remember, there are two kinds of naming. And one is going to be ionic. In ionic, we need to have an ionic table. So let's look at some examples here. So we have molecular, ionic compounds. Molecular are non-metal to non-metal. Ionic are metal to non-metal. Okay, so let's look at P6 Cl5. Okay, and do I have a periodic table? I don't have a periodic table. I need a periodic. Let me go grab a periodic table real quick. Where is a periodic table? Okay. And then we have so we have metals, non-metals. Okay, so P, phosphorus, and chlorine. Okay, phosphorus and chlorine. So that's two non-metals. That means that's going to take on the covalent naming structure. So it's going to be phosphorus. And there are 6 of them, so that's hexaphosphorus. And there are 5 chlorides. Now these are ides, the second part. And these are the names of the ides up here. And there are 5 of those, so that's penta. So that's hexaphosphorus, pentachloride, hexaphosphorus, pentachloride. Now, whenever we have non-metal to non-metal, we have to always have the prefix giving us a number. Mono is optional. Mono is not optional. Okay, when it's the second one, it's never optional. The first one can be optional. So if we had, that could either be monophosphorus hexachloride or phosphorus hexachloride, because there's just one of these. Okay. Let's do so let's name this. Okay, well, this is a metal and a non-metal a metal cation and a non-metal polyatomic anion. Okay, polyatomic ones are the ones that have lots and lots of oxygen variations. Okay, so this is aluminum. Sulfate. Now, the first question is, I wrote AlSO4. Is that a legal formula?
Yes.
Why do you say yes?
Well, we have the metal cation and the non-metal anion, and they like to pair up.
That's right. There's one more requirement, though. If it's a metal cation and a non-metal anion, that means the charges, because there's ions now, those charges have to be net zero. So if you look at the charge on aluminum, it is +3. There, +3. Sulfate is -2. So do those cancel each other out?
No.
Correct, they don't. So we've got to modify the subscripts here to make them cancel out. So how many aluminums do we need against the sulfates? 1-to-1 obviously doesn't work because it's a +3 and -2. So what do we have to do to modify that? Remember the 3 and the 2 in the common denominator, 6. So how many aluminums at +3 do we need to make 6?
2.
And how many -2s do we need to get up to 6?
3.
Correct. So that's the formula for aluminum sulfate. Okay, so that's now a -6 and that's a +6. So whenever we do ionic compounds, the metal plus the non-metal, we have to make sure that we have a charge net of 0. Charge net of 0. Now the reason for that, nature does not like isolated charges. Those are horrendously unstable. So if this was AlSO4 in nature, it would immediately revert to this. Okay, what is the name of that? Well, we have copper and we have sulfur. First of all, copper is metal. Let's see, where is our periodic table? It is over here. So here we have copper, and here we have sulfur. Well, sulfur is non. Okay, and metals form cations. Non-metals form anions. And sulfur is a -2. However, copper comes two ways. Copper comes +1 and +2. Cuprous, cupric. So we have copper. Okay, so if it was copper +2, what would the formula be between the two? This guy here. What would the formula be with copper +2 and sulfide -2? Well, remember net 0 +2 -2, does that add up to 0?
It does, yes.
So that means that's the way we'd write it. What about copper +1 and sulfide -2? What do we have to do to modify that so it adds up to net 0?
We would find the common denominator, which is 2.
Yeah. So how many ones we need in 2?
2.
Yeah. So that's the formula if it's +1. So then obviously this is copper +1, not copper +2. Copper +1 is written two ways. Copper parentheses and this means +1 charge. The other way to write it is cuprous sulfide. Okay, and both those come off of this guy here. Copper 1 and cuprous. And you need to, whenever you're writing ionic binary names, is some of the cations have two names. And sometimes on a test, you may be asked, if there are two names, write both names for full credit. That's the way I would word it. So in this case, you'd have to say copper 1 sulfide, cuprous sulfide. Over here. Now, I gave you a whole bunch of worksheets on this as well to practice. So you just need to keep practicing on these. Now, one other thing, remember from last time I mentioned beryllium. Beryllium is not on this chart. But it's in group 2. And all group 2s are +2. So it's in the same chart as barium, calcium, strontium. Okay, so check the periodic table before you make a decision. Always double check if it's not on the common ion chart. Just find it on the periodic table and see where it lies relative to the group. Okay, all right, so that's what I wanted to cover today. Those are the 4 main things we talked about in Unit 3. Looking at naming binary compounds, both ionic and molecular, doing structures of Lewis dot structures, doing 3-dimensional Vesper structures. Now, between now and Wednesday, if you'd like to have a private Zoom session or a small group Zoom session, you just have some real issues with some problems, that's fine. Just let me know. Be glad to work that. Okay.
Question, do we need to remember all the common ions from
No,
the chart?
no.
Or
you-
can we print that out
yeah,
and use it for
yeah.
the test?
Yes, yes, you may. Yeah, and the when you see the test, it'll say you may use your notes. Okay, Caitlin?